Hello everyone. In today's lecture, we will discuss Gibbs-Helmholtz equation. And this point is from chapter number 2, second law of thermodynamics. And we have already discussed Gibbs free energy and Helmholtz free energy in the previous lecture. From Gibbs free energy function, G is equal to H minus Ts. This is the relation between the quantities delta G, delta H and delta S can be obtained. That is, we have seen one equation. Delta G is equal to delta H minus T delta S. Similarly, the quantities delta A, delta E and delta S can be related with the work function. And these are given by equation A is equal to E minus Ts, or delta A is equal to delta E minus T delta S. So this is the definition of Helmholtz equation or the Helmholtz free energy. A is for Helmholtz free energy and G is for Gibbs free energy. And the relations between the above thermodynamic function leads to two important relations. Each of them two relations is known as Gibbs-Helmholtz equation, and it is the one of the most important relations in chemical thermodynamics because it helps us towards a better understanding of the driving force behind chemical reactions. The two relations may be derived as under. We know that at a constant pressure, dG is equal to Vdp minus SdT, and dG at a constant pressure is equal to minus SdT at a constant pressure. Or this equation can be written as dG divided by dt at constant pressure is equal to minus S. This equation shows the rate of change of Gibbs free energy with respect to change in temperature at a constant pressure and is equal to minus S, that is entropy. Now we will see the actual derivation or the actual equation of Gibbs-Helmholtz equation. So Gibbs free energy change for a chemical reaction. Let us consider a general reaction. AA plus BB gives CC plus DD. Here, small a, B, C and D represents the number of moles and capital A and capital B represents the reactants and capital C and capital D represents the products. So, for this capital A, B, C and D, we have to find out Gibbs free energies. So, consider the Gibbs free energies for reactant and products as here Ga and Gb are the Gibbs free energies for reactant A and reactant B, and Gc and Gd are the Gibbs free energies of products. So, let Ga, Gb, Gc and Gd are the Gibbs free energy per mole of a substance A, B, C, D. Now, if delta G is the free energy change of a chemical reaction, then delta G is equal to summation of Gibbs free energy of the products minus summation of Gibbs free energy of the reactants. So, this is our equation number 1. But we know the equation summation of G products or the Gibbs free energy of products is equal to CGC plus DGD. Here GC and GD represents the Gibbs free energies of a product C and D, and here small c and D are the number of moles of the species capital C and D respectively. So this is for products. Same way we can write the equation for reactants. Summation of Gibbs free energy of reactants is equal to AGA plus BGB. J and GB are the Gibbs free energies of the reactants A and B, and small a and b are the number of moles of capital A and B. Then substituting the values in the first expression. So this is our first expression. Just put these values in this. Substituting the values in the first expression, we get delta G is equal to CGC plus DGD minus AGA plus BGB. So first bracket is for the product and second bracket is for the reactant. So Gibbs free energy of a product minus Gibbs free energy of the reactants. This is our equation number 2. For an isothermal process, delta G is given by delta G is equal to delta H minus T delta S. Here delta G represents the change in Gibbs free energy, delta H is for change in enthalpy, T is the temperature, and delta S represents the change in thermodynamic entropy. So this is our equation number 3. Now delta H and delta S are the change in enthalpy and entropy of the reaction. Now differentiate the equation number 2 with respect to temperature and the pressure will be constant. So our equation number 2 is this, and just we are going to differentiate this equation number 2 with respect to temperature and keep the pressure constant. After differentiation of equation 2, we will get delta or delta G divided by del T at a constant pressure. That is change in Gibbs free energy with respect to change in temperature at a constant pressure is equal to, just divide each parameter from this equation by dt at a constant pressure. The equation will be as C del Gc divided by del T at a constant pressure plus d small d in bracket del Gd divided by del T at a constant pressure. This is for the product minus reactant. Same way you can write equation for reactant. Del Ga divided by del T at constant pressure plus B del Gb divided by del T at constant pressure. So this is our equation number 4. But del G divided by del T at a constant pressure is equal to minus S. This is the entropy. So this minus S represents the entropy. Now just put del G divided by del T at a constant pressure is equal to minus S. So equation 4 became delta G divided by del T at a constant pressure is equal to, just put this term is equal to entropy, and equation will be as this, minus CSC minus DSD, this is the first bracket, minus in second bracket minus ASA minus BSB. The equation can be written as delta G divided by del T at a constant pressure is equal to, in a bracket, minus summation of S products minus in second bracket minus summation of S reactants. So this C and D species represents the product. So you can write for the first bracket minus summation of S products, and for the second bracket here capital A and capital B represents the reactants. So in bracket you can write minus summation of S reactants. So this is our equation number 5. So you can write this equation as, take minus sign outside the bracket and in bracket plus summation of S products first and minus summation of S reactants. So this is our equation, and summation of entropy of product minus summation of entropy of a reactant, this can be denoted by delta S. So just put instead of that delta S. So left side will be remain as it is, delta G divided by del T at constant ratio is equal to minus delta S. So this one is our equation 6. Now substituting the values of delta S in equation 1, we get. So see, our equation number 1 is here. Delta G is equal to summation of G products minus G reactants. So our equation is as delta G is equal to delta H plus T delta S. So our equation is here. Instead of 1, you can write equation number 3. Delta G is equal to delta H minus T delta S. Now we have value of a delta S. So just put value of delta S here and write the equation. So delta G is equal to delta H plus T delta S. Instead of delta S, you can write the value. So here is the minus T delta S. Minus minus become positive. So plus in a bracket del delta G divided by del T at a constant pressure. This is kept here. And the equation number 7 is this, and this is known as Gibbs-Helmholtz equation. And it establishes the relationship between free energy and enthalpy of a given reaction, and it is applicable to a chemical as well as physical changes. And the Gibbs-Helmholtz equation demonstrates the effect of temperature on free energy of a given reaction or physical change. And del delta G divided by del T is known as a temperature coefficient of a reaction. And the alternative expression for the Gibbs-Helmholtz equation is here. So the another expression which shows delta G changes with respect to temperature, and this can be derived as this way. So del delta G divided by T and this bracket complete divided by del T and all this at a constant pressure is equal to T in bracket del delta G divided by del T at a constant pressure minus delta G divided by T square. So we have the equation delta G is equal to delta H plus T delta G divided by del T at a constant pressure. Oh, this is our equation number 7. Take on as it is here. This one. So T del delta G divided by del T at a constant pressure is equal to delta G minus delta H. And substituting this equation in equation number 7, we will get equation as del delta G divided by T and whole terms divided by del T at a constant pressure, which is equal to minus delta H upon T square. This is our equation number 8, and this equation is again known as the Gibbs-Helmholtz equation. So there are two equations. Del G is equal to del H plus T in a bracket del delta G divided by del T at constant pressure. This is our first equation, and second equation is this one. Del in a bracket del delta G divided by T bracket complete divided by del T at a constant pressure is equal to minus delta H upon T square. So this is our second equation, and these two equations are called as the Gibbs-Helmholtz equations.